And I also apologize, I didn't get a chance to make a video for the whole quotient rule and product rule thing. It's just kind of the way it worked out. But I'm not using anyone's notes today, I'm just using my own, so I don't have to worry about posting this video, copyright rules and all that. So let me first present the need for the chain rule. So let's say you're doing this problem, x squared plus 3x, right? And this was cubed. You can actually solve this problem without any new rules. You can just kind of cube it out. So it's going to be x squared cubed plus, and then there's a Pascal number, x squared squared times 3x to the first plus, and then another Pascal number, x squared to the first times 3x squared, finally plus, and this is our last term, last term is a 1 in front, and then it's just 3x to the third. So all this boils out to x to the sixth plus 9, x to the fifth plus 27, x to the fourth plus 27, x cubed. And that's not a derivative, but here comes the derivative now. So I rewrote it nicely, and I got 6x to the fifth plus 45 x to the fourth plus 108 x cubed plus 81 x squared. Okay? Everybody with me? Okay, now this also factors. All right? So far it's already been a lot of work just to get the derivative. And this actually does factor very nicely. After some playing around with it, you'll finally get it to factor to look like this. You can actually pull out a 3. Okay? And an x squared if you like. But you can pull out a 3. I think I will pull out the x squared, sorry. I was debating if I wanted to, but I think I do want to. I'll pull out 3x squared. So this is going to become 2x cubed plus 15x squared plus 36x yeah, 3 times 36 is 108 plus 27 everybody with me? Okay, and then this factors on the inside. Does anyone see how to factor that? P's and Q's maybe? You guys remember P's and Q's? Why don't you guys try P's and Q's on it real quick. See if you can get it to factor. I'll pause the video. You try P's and Q's on it. Okay, so we tried it on the board there, and we found out that x minus 3 actually factors out, leaving us with 2x squared plus 9x plus 9. And Matt says that factors even more.
Wouldn't that x minus 3 go to x plus 3? Because
I'm sorry, x plus 3. Negative 3 was the root. X plus 3 is the factor. Thank you. And then this factors into 2x plus 3 times x plus 3. So I think we finally got our answers. A lot of work. We basically got, let's see what we got. We have a 3x squared, there's an x plus 3 squared, there's a 2x plus 3, does that look right? What a pain. Okay, so this is a lot of work. First we FOILed, then we differentiated, and then we tried to refactor it. Okay? Let me show you how you would treat this with the chain rule. Same problem. X squared plus 3x is cubed, right? This is the problem. Now let's say you taught the power rule to a 7th grader. So you go up to a 7th grader and you say, hey, you want to learn some calculus? And they're like, what's in it for me? You say, well, you'll be the smartest kid in your class. You're like, sweet. I want to be the smartest kid in my class for a day. Teach me how to find a derivative. So you're like, okay, it's really simple. I'll show you an example. Okay, watch. Let's pretend you have x cubed. What's that mean? Oh yeah, you're in 7th grade. Let's just say you have it, and you don't even know what it means. You can still find the derivative. Okay, kid? All right. What's x cubed? Don't worry about it. Watch. You're just going to put the 3 in front, okay? Okay, I can do that. And then you're going to take away a power. What do you mean? Just like, what's 3 minus 2, kid? 2. 3, what's 3? What's 3 take away 1, kid? 2. That's it, that's what I meant, take away a power. Oh, you mean like subtract 1 from the power? Yes. Well, there you go, you just found the derivative, kid. Oh, I feel so smart. All right, kid, try it with this, 5x to the 6th. What do I do with the 5? Just leave it there. So I bring down the 6? Yeah. Do I add it? No. Multiply it? Yeah. All right, 30. X. You forgot the power. What's the power? 1 less, remember? Oh yeah, 5. Think you got it? I got it. Go show a friend. Okay. You can teach a kid that, right? They don't have to know what it means. You can teach a child that. So you come back to them the next day, and you give them this problem in black. What's the kid going to do? He's going to bring that 3 down, because that's kind of what you told him, right? Then he's going to go ahead and take away a power, making it a 2. He'll probably stop thinking he's done. Is he done? He's not done. You can't just ignore the inside and pretend it was just x cubed. It's not x cubed. It's x squared plus 3x cubed, right? So the ironic thing here is this is most of the answer. Okay? What you haven't looked at is the inside yet. You can't totally ignore it forever. So far we've ignored it, and we're getting the right answer. We're just not done yet. We need to now look at the inside and find the derivative. So what's on the inside? What's the inside function? X squared plus 3x. What's the derivative of that? 2x plus 3. If you just simply tack that on by multiplication, this is the answer. It's the same answer we just wrote on the previous page, except the previous page has another x squared factored out. But this is the same answer we just got after all that hard work. And don't forget to title it. This is f prime, of course. Okay, so what is this thing? This is like what I like to call the derivative of the outer function. You're just sort of ignoring what's on the inside, and you bring the power down, take away power. I call that the macro function, the outer function. Then you look on the inside. What's this 2x plus 3? That's pretty obvious what that is. What is that thing? That's the derivative of the inside. So I call that the micro function. Okay? The inside guy. So this is the derivative of the outside, derivative of outer function. This is the derivative of the inner function. And how are they connected? What's between them? What math symbol is between them? Very important. Multiplication. Okay? So don't add it on. Multiply it on. Okay? Okay, so let me give you a real life example of this that might help you kind of understand why this works. Or maybe this analogy won't help you at all. Let's say you have a friend riding a unicycle. Anyone have a friend who rides a unicycle? Unicycle. Jordan, can you ride a unicycle? That is really cool. That is really cool. So you have a friend riding a unicycle. We'll draw the person. Here's the unicycle. It's going to the left. Okay? Hanging on to the back, don't try this at home, is a kid on a skateboard. Okay? Hanging on to the back. The wheels are obviously smaller, right? And since the kid is very small, he's decided to take his teddy bear along. And the teddy bear is on a really small skateboard being pulled along. Okay? Now, whose wheels are spinning the fastest? The teddy bear's wheels are spinning the fastest. Not going the fastest. They're all holding together, so they're all traveling along the road at the same speed. But if you've ever held onto the back of something while you're on your skateboard, your wheels spin a lot faster than the object you're holding onto. Like if you're holding onto a bicycle, the wheels are just going dee-dee-dee on the bike, and the skateboard wheels are going. Okay, you're probably getting like speed bubbles. If you've done it before, you know what I'm talking about. And the teddy bear's wheels are spinning around really fast, and it's because of the radius of the wheels. In fact, you can even say that when a wheel is twice as large, it spins half as fast. Okay? So it actually works that easily. So let's say that this wheel is 10 times bigger than the skateboard wheel. The skateboard wheel will spin 10 times faster. 10 times as many turns in a minute. 10 RPM, 10 times the RPMs. And then let's say that the little teddy bear's wheels are 10 times smaller than the skateboard wheel is. That's going to spin 100 times faster than the unicycle wheel. Okay? So it's like a chain effect. All right? In this chain, we have a unicycle and two skateboards. The rate of change of the skateboard wheels, it's actually the rate of change of the angle on the skateboard wheels, is 10 times 10. It's basically a compounding effect. And this is kind of the way it works with functions. If you want to measure the slope on a function, but there's a function buried inside the function, the derivative of the outer function, the derivative of the outer function will combine by multiplication to create a stretching effect on the derivative. So basically, the wheels aren't the best analogy, but it's the best I can think of. The steepness of a curve is affected by both the overall look and the ingredients. So the slopes get compounded by multiplication. So all you do is you take the derivative of all the involved functions and multiply them. Okay? This rule is very, very powerful. And it was fast, really fast. Let's just look at another example. Let's say that you were given f of x equals x squared plus 3x, not to the third, but to the 100th. Now your whole option of getting out Pascal's triangle are not so very wise. If you use Pascal's triangle on this, you'll get 101 distinct terms. If you don't know Pascal's triangle, you have to create all 200 terms and collapse it down into 101 terms. But once you have your 101 terms, take the derivative, you probably made a mistake somewhere anyway, right? And you don't get a factored answer. Good luck factoring it. Okay? If you do it by the chain rule, and you find the derivative, you do it this way. Watch. Bring down the 100, decrease the power of the x squared plus 3x to 99, multiply by 2x plus 3, because that's the derivative of the inside. This also has all the right terms, but it's factored, and it's done. And it measures the slope of f. That's awesome. So like Demoivre's theorem, we have a really nice option to foiling. Demoivre's theorem is where we multiplied, 1 plus 5i times itself 1,000 times. Polar form was the way to go, remember? Okay, so this is kind of like that in a way. That's a huge time saver. Here's another reason why you might want to use it. Let's say that the problem doesn't say x squared plus 3x to the 100, but x squared plus 3x to the half. Now you can't even use Pascal's triangle if you wanted to. What does this even mean? X squared plus 3x times itself half a time? Doesn't make any sense, right? Fractional exponents don't mean quite what you think they mean, It's not like you're multiplying this by itself 100 times anymore. You're not even multiplying by itself. You're trying to find what two things multiplied by themselves, what two equal objects multiplied by themselves makes x squared plus 3x. It's complicated. But let's say we can still find the derivative. The chain rule bails us out. Bring down the half. Diminish your power on this x squared plus 3x by taking away 1. So take away a power. What do you got? Negative 1/2. Don't ignore the inside forever. It's time to look at the inside. The inside says x squared plus 3x. The derivative of that's 2x plus 3. Attach it by multiplication. You're done. It's a very powerful trick. Okay? How about this one? F of x equals sine of x squared. Now, I'm not going to lie to you. You can still use limo, f of x plus h, minus f of x, all over h. How many of you like using that rule? Limo, f of x plus h minus f of x all over h. Anyone like that rule? Nobody likes that rule. That's the definition of derivative, and it works on every problem. Definitions always work, always. Okay? But none of the shortcuts we've seen the last couple of days would ever handle this problem. Even if you know the derivative of sine is cosine, that's for sine x, not for sine x squared. See the problem? But if you look at it as, hey, I've got a sine x on the outside and an x squared on the inside, you can use the chain rule. Is the answer just maybe as simple as cosine x squared? After all, the derivative of sine is cosine. Is that the end of it? If you thought that was the right answer, know that you have part of the answer. You also need to look at the inside. Inside, we have this function called x squared, and what is its derivative? 2x. Now you're done. The cosine is the derivative of what? Sine. And the 2x is the derivative of what? X squared. The outer function, the inner function. Notice that when you take the derivative of sine x squared, you actually write cos x squared. It's not like you change the angle in the sine. You still keep the x squared. Derivative of sine x squared is cos x squared times, and then the 2x.
Oh, because x squared is essentially still a number?
It's an angle.
It's just like...
Yeah, you don't change the angle. Sine x differentiate. The derivative of sine x is cos x. You didn't change the angle, right? So we have to keep it as cos x squared, but then we have to, as an afterthought, multiply on 2x. Okay, this is going to get a lot more complicated, but the rule is clear. You take the derivative of every nested function and multiply it on to the originals, right? How about this one? F of x equals, how crazy do we want to go here? Let's do this one. The cube root of x squared plus 3x over x minus 5 plus 4. Okay, when you first see this problem, you might think, oh, a quotient rule problem. Well, not really. Primarily, this is a cube root problem. The outer function here is a cube root symbol. So I think we should treat it like that. I think we should think of it as a cube root problem first and foremost. Do you remember what would happen if you gave this to a 7th grader? What would they do? They'd bring the 1/3 down. That's exactly the correct first step. So that's exactly what I'm going to do too. You bring that thing down, and then you diminish the power by 1. Well, I guess we have to copy all this garbage. What does it give us if we diminish our power by 1? Negative 2/3, right. But so far we've ignored the inside completely. The inside is this function. It's composed inside the other, you know. So now we need the derivative of that. I think the 4 part's going to be easy. What's the derivative of that plus 4? Okay, why don't we put that in? We'll feel good about ourselves at least. We'll put a plus 0 there. That's the derivative of the 4. What about this x squared plus 3x over x minus 5 business? What do we do with that? Quotient rule. Right? Our job is to find the derivative of this yellow. What would you have done last night? Quotient rule, right? Who cares about the 4, right? Nobody cares about the 4. Okay, so it's time to find the derivative of the yellow expression. We're going to use low d high minus high d low over low squared, and then plus 0 for that plus 4. Okay, here we go. Low and high. Don't worry about the plus 4. So low is x minus 5. D high is 2x plus 3. Minus high, that's x squared plus 3x. D low, that's just 1. The derivative of the bottom there is literally just uno. All over what? Low squared. And remember, I'm not too strict about you cleaning it up. In fact, it's very hard to clean this up. There's not really that much you can do. If you want to foil some of this red, you can. But you're not going to be able to do anything with this anyway. This other part, this part that has the weird power. And remember, our ultimate goal is to measure slopes, which means we'll probably be plugging numbers in. 0 or 1, hopefully. Oftentimes, that's all it is. Plug in 0 or 1. Yeah. Because on the AP exam, they don't care if you plug in complex numbers, you know, like 15.6. They just want you to understand, and then, you know, if you plug in, if your expression's wrong in the slightest, and you plug in 0, you're going to get the wrong answer. So if the expression's perfect, they'll just let you plug in 0. It's nice and easy. I think you just get 4/3. Actually, you get 0 for everything. For this one. No, you don't. I think you get like 20 or something. But anyway, my point is, usually you just plug in numbers, so don't get carried away. Simplifying. But that was technically, was that a chain rule problem or was that a quotient rule problem? It's kind of both, right? All right. Let's try a chain slash product rule problem. Okay. You guys are getting into the advanced stuff here. Let's say you're given, I know. How about x sine x and it's square rooted? Okay, so this is your function. The instructions are all the same today. Find the derivative, find the derivative, find the derivative. Okay? Primarily, is this an x problem, a sine x problem, or a square root problem? On the outside, without knowing what's on the inside, the outside of this is a square root problem. I think we should write it as blah blah to the half. Okay? Blah half power. Okay? If you gave this to a 7th grader, they would bring that half down. They would subtract 1. It would take them a while to figure out, but it's negative half. They're 7th grade. Okay? But you can't ignore the inside forever. And now it's time. Look at the inner expression. The inner function is that thing. X sine x. That's going to go here. The derivative will go here. Don't forget the parentheses, by the way. It's very important. Why did I give myself so much room for that? Isn't it just like x cosec or something? Yeah, we've got to be careful. This is the function x times the function sine x. You have to use the product rule here. You cannot just say, oh, it's x cosec. No. X sine x. So you're going to do the derivative of x times sine x plus the derivative of sine x times x. You're going to do the product rule. Okay, so let's do a little detour calculation here so we can fill that green in. The function is x times sine x. You do kind of a left times the derivative of the right plus the right function times the derivative of the left. So x is just the f function. The cosine there, that's g prime. And then here we have g, and this is f prime. The 1 is f prime. Okay, I guess that's what goes in the green up there. So the final answer is 1/2 x sine x to the negative half, and then x cosec plus sine x. And they'll probably make you plug in pi over 2 or something, or pi over 4, you know. Something easy to work with, probably. Or they'll give you a calculator and say plug in, 16 degrees or something. Actually, there's no degrees on the AP test. Plug in, pi over 12 radians or something. But you can get a calculator and do that. Okay? That was a combo of what? Yeah, product rule and chain rule. You can tell it's a chain rule because there's a composition. There's like something inside of something. And you can tell it's a product rule because one of the ingredients had two functions multiplied. So now you realize you can make these as complicated as you want, right? How about this one? Square root of tan x. You say, Mr. Shore, that is not fair. That's not fair at all. Even if, Mr. Shore, I write this as tan x to the half. And even if a 7th grader would bring down the half and take away 1, this just isn't fair. How do you expect me to find the derivative of tan x to place it here? I'm glad you asked. That'll work. Tan of x plus h minus tan of x all over h. Limo that thing. That'll work. That will be very hard. You can use your special limits, though. Oh, wait, I thought the special limits I taught you were like sine h over h, cos h minus 1 over h. Okay, that's what we need to think. We need to think, wait a minute, tangent's new, but it is a quotient. Isn't tangent a quotient?
Yeah.
It's sine x over cosec, folks. Write it. We need to do a detour problem. To get this green figured out, we need to think, hey, look, tan x is just sine x over cos x. We have a beautiful quotient rule for this sort of thing, right? let's give this a name so we have everything titled. What do you guys want to call tan x right now? F, G, probably not F. G? Okay, so this will be G. We need G prime. So quotient rule is the best suited for this. Low D high minus high D low over low squared. Okay, low, I say it, you fill it in, okay? Low cos x. D high, the derivative of the top. Cos x, good. Minus high, good. D low. Yeah, hopefully you did your worksheet and you know that the derivative of cosine is negative sine. So when I say D low, you'll know, oh, that's negative sine. I just put it right there. All over low squared, which is cos squared. Some of you are smiling. I think I know why. What is that top? 1. Yes, it is. Sine squared plus cosine squared is 1. What's another way to write 1 over cos squared? Sec squared. There, you just learned a new derivative. What's the derivative of tangent? Sec squared.
We can have that one memorized, yeah, and like.
Yes, you certainly can. Memorize as many as you can.
Well, because
I will summarize too. On Tuesday when I see you next, we'll write down all the ones we think we can memorize. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of tangent is sec squared. Yeah.
on the AP test, would we have to show our work for the derivative if we
No.
get something?
If you know the derivative of tan x is sec squared x, you just plug it in. I'm going to need you to know that. You don't have time to redo this. This probably would have gone a little faster if we didn't have to do this little detour, right? Well, most people memorize the derivative of tangent sec squared, and you just use it whenever it shows up. But look at the answer. That really wasn't very complicated. We started off by saying, hey, that's kind of a square root problem, so we brought down the half to with power. When we got to the inside, we got a little stuck. But we used quotient rule to figure it out, right? So in other words, we have all the tricks we need. There's only one style of problem you cannot handle right now, actually. Well, there's two. You won't be able to do this, okay? If I give you this and I say, what's the derivative? You won't know because this is not a situation that we've seen. It's the x is upstairs, you know? What do you do with that? Or even worse, how would you find the derivative of x to the sine x? This is where I want to start BC next year. Mr. Lynch will start over for most of this. Maybe not limits, okay? But AB will be basically, let's redo the derivative, let's figure it out and all that. BC, we're going to jump right into these things we can't do. Like, how do you find the derivative of how do you find the derivative of x to the sine x? This is not something times something, it's not something divided by something, and it's not something inside of something. Well, it's kind of something inside of something. But how do you work with power and base at the same time? Okay, you have a question?
Yeah, do we have a summer assignment for AP?
Basically, you're going to have a summer assignment, yeah.
Just do a bunch of tutorials.
No, you're going to be watching all of Chapter 2 videos,
Oh, that you made?
all the calc videos for Chapter 2. I'm not teaching Chapter 2 next year, and half of Chapter 3.
Or taking notes on it and watching
Yeah.
videos.
AP English, you read lots of books. AP Calc, BC, you watch lots of videos, take lots of notes, and do lots of worksheets.
Okay,
Yeah. And you need to get your book before the summer.
okay.
Take it home and do problems out of Chapter 2. We're skipping a chapter or a chapter and a half. We're jumping into Chapter 3B, the end of Chapter 3, because I'm done teaching a BC class that runs right up to 3 weeks before the test. That shouldn't be happening. It doesn't happen in any other school. BC always starts later in the book. Okay, there's a lot more to learn after the Calc AB stuff. So, okay, that's my expectation. I'll figure it out. So the chain rule is going to allow us to undo problems that are way more complicated than anything else. So this brings up a question. What happens, like how do you know when you're done? Like what if you have a problem like this? Sine of, and then let's say you have x squared cosine of root x. See, this is at least a double chain rule. I'll tell you why. First of all, there's a sine function clearly here, and inside the sine function is a product rule problem. But if you look carefully at the product rule problem, one of the ingredients, cos rad x, has an inner function called rad x. So this thing is nested beyond belief. It's hopeless, almost, it looks like. But we can actually very carefully unravel this whole thing. So I do want to do this last example because it shows you that you can use the chain rule more than once, and it kind of also tells us when to stop. Because some people go too far with the chain rule. All right? Okay, so what's the general idea? Leibniz would write it this way. Leibniz would say this: if you want to take the derivative, okay, of f of g of something, okay, you will first pretend that g is like an x. Okay? G of x. Just think of it as x. In other words, sort of ignore it. And so you're going to find df, sure enough, but you're going to just treat g as your x. So you're going to find df dg. Then you're going to look at g more carefully and take its derivative using x as your variable. Okay? That's the chain rule in Leibniz notation. Lagrange would write it this way. Lagrange would say, oh, you have a function, I see, and it's got g of x inside of it, stuck inside, and you wish to prime it. Well, let's f prime first. We'll keep the g of x stuck inside, and then we'll multiply by g prime. These are exactly the same expressions. What you're looking at here, this is how Leibniz would write it, this is how Lagrange would write it. They're both dot chain rule. Dot chain rule. Okay? Get used to seeing it. When you see that, you're supposed to say, oh, the chain rule. I recognize that. If you look at the first Leibniz one, it's kind of cool. If you just mentally cross out the dg's, you get df dx, which means you found the derivative. But don't cross them out, okay? Just think it. Think it. These two kind of mentally at least cross out and gives you df dx, which is what you're seeking for, right? This one's a little more cryptic looking, but it's more commonly used. So you kind of need to know both. All right. How do you handle this problem? Well, first and foremost, you look at the outside. This is a sine blah problem, right? Sine blah. So let's call this f, right? Don't forget to title. So when we start to do f prime, we first notice, hey, this is a sine blah problem, so we're going to write cos blah. That's the first step. The first link in the chain. The derivative of sine blah is always cos blah. Okay? But you've totally ignored the inside. That's called finding df dg. Okay, now we're going to look at the inside. The inside is this green thing. I think it deserves its own product rule, don't you? Okay, so let's do a little detour. X squared cos rad x. We're going to ddx that thing. We're going to take its derivative, see? Let's see. Product rule. Parentheses, parentheses, plus parentheses, parentheses. Maybe give yourself a little more room than that. I'll rewrite that. Parentheses, parentheses, plus parentheses, parentheses. I'm kind of tired of not having enough space and having to redraw them. Okay, let's try it out here. You're supposed to think of it as x squared times cos rad x, right? Okay. So let's take the derivative of x squared, and then we'll multiply by cos rad x, and then we'll take the derivative of cos rad x, and we'll multiply by x squared. Okay, so it's going to be derivative of x squared is 2x, okay? And then we write cos rad x. And then we switch it up. So now we're going to do x squared times the derivative of cos rad x. Uh-oh. The derivative of cos rad x. Oh man, another detour problem. We've got to find the derivative of cos rad x. Well, I can assure you one thing, it's going to be a negative sine, right? So it's going to be a negative sine rad x, but it has an inside, doesn't it? What about the rad x? Did we take the derivative of that yet? No. So we need to take the derivative of rad x. Do you guys remember what it is?
1/2 x to the negative.
Yeah, it's 1 over 2 rad x, if you want to memorize that, or just think of it as x to the half. Okay, so there's one more little guy right here, and it's a 1 over 2 rad x. Why am I putting that in? Because I can't just very well take the derivative of sine cos rad x and call it negative sine rad x. I can't do that. I can say the derivative of cos rad x is negative sine rad x times the derivative of rad x. So there's your little derivative of rad x there. And that is what gets attached to our answer that we were writing a moment ago. This was our answer. We did take a little detour, remember? So now we need to go back and finish it up. So what goes here? Lots of stuff. 2x cos rad x plus x squared. I guess it's really a minus. I meant to say minus x squared cos rad x times 1 over 2 rad x.
No, negatives, or sign, right?
Oh, thank you. This one's a sign. Yeah. I was just trying to copy the green-purple statement here into this bracket. And I made a copy here, thank you. That's a times, that last thing there. What a mess, huh? But that's his job. He measures slope, right? And you could plug in 0 or pi or whatever they ask for. Question?
How does it multiply the 1 over 2 rad x by the x squared?
Okay, so how do we know when we're done? This is a very important question, right? Are you thinking we still need to do something else now?
Well, like,
Are there more links in the chain?
because you have the negative sine rad x times 1 over 2 rad x in parentheses. And you have the x squared.
Yeah, but I already multiplied with that x squared, it's right there.
So it doesn't have to, well, never mind.
Oh, a times, that's a good question. So x times a times b is just xab. It's not xa, xb.
Oh,
You know what I mean? Yeah. So don't FOIL it. You don't distribute. You only distribute when you're multiplying into a sum or a difference. But this is just a times times situation. Times times. So ABC is ABC. It's not AB, AC. Yeah. Good question. So what happens is, as you play around with these and stuff, you're never quite sure if you're getting them perfectly right until you really master it, and then you're like, okay, I know I caught everything there. If you're real slow and careful, you'll catch it all. If you're too slow, you'll forget what you're doing, and you'll miss something, or you'll do too much, okay? So some people are like, oh, I'm pretty sure there's something else I'm supposed to do. Not anymore. Let me ask you what functions you see here. Everyone see a sine graph, or a sine function here? Okay. Everyone see 2x squared quadratic? It's in here, right? There's a quadratic? Okay. There's a cosine function? There's a rad x function? Okay. Did we, at some point, differentiate or take the derivative of a sine? Okay, then we did. We caught that link in the chain. Did we ever take a derivative of an x squared? Does anybody remember doing that?
yes.
We did. Okay, then we caught that link in the chain. Did we ever take the derivative of a cosine at any given time? We did. It was right here when we made negative sign right there. Did we ever take the derivative of a rad x? Did we ever do that? We did. We caught it all. Okay, so don't be deceived. It's just the functions that exist. Don't do anything extra. I guess if you really want to, there's an innermost function called x. I guess we never took his derivative, but that's just 1. So if you want to put a big fat times 1 out here, go for it. But who does that, right? So it's kind of hard to know if you're done or not. Just go through the mental checklist. Say, did I take a derivative of an x squared? Yes, I did. Did I take a derivative of rad x? Yes, I did. How about a cosine? Yes. How about a sine? Yes. And then you know you at least got all the steps. Is it all in the right order? Hopefully you work from outside to inside. Okay.
So is that why on the BC calc test you have to go like 4 decimal places? This is going to be a number between -1 and 1. And
Oh, yeah. The answers for this, first, the answer for the function, sine has always been -1 and 1. Are you saying the slopes are too?
no, cos, this is a cos, everything else, so it should be.
Yeah, this is a cos times a bunch of garbage. And then all this garbage is less than 1. Because the cosine is going to spit out numbers less than 1. Absolute value is less than 1. Same thing here.
So
I don't know what that, doesn't that x squared affect anything? The x squared might make things grow a little.
I thought it was.
But the accuracy is important on the AP test. Yes, it is.
I thought it was.
Nearest thousandth for everything.
I thought this was a cos, and then like big parentheses, all of this, and then end parentheses.
No, no, no. The cosine, this is a cosine of x squared, cos rad x. Stop. Multiply that on to this. Okay? This is not like cosine of one big expression. It's cosine of a messy times some other messy stuff. Okay, let's check it. Let's see what it comes out to numerically. Let's say at x equals 1. Okay? Let me show you how to do that on your calculator. So you can pull out your calculator. Even the TI-84 can do this, okay? So bust out the calculator. Good morning, Rabbit Emu. Okay, turn it on. Now you can do this from the home screen, or you can type it in as a graph. It doesn't really matter. I'm going to do it as a graph. So I'm going to type very carefully sine of what? X squared times cos rad x. And I'm really not interested in the graph. I couldn't care less about the graph right now. I was hoping to just find the derivative at some number. Now if you have a TI-89 and you press find the derivative, it will spit out that answer we just created. It's crazy. The calculator can actually find derivatives and write them out for you. It's amazing,
Is that
actually.
N derivative?
Huh?
Is that N derivative? Is that the
No. Under calculus option 1,
differentiate?
yes. It will find the derivative and spit out the actual expression. But if you have a TI-84 or one of the non-CAS type calculators, like most of us do, you can at least get the derivative at any value you want. So you can find the slope at 4 or find the slope at 10, okay? And that's pretty valuable too. Okay, so what I usually do is I go back to the home screen to do this. And then I go to Math, and you got to scroll down to option 8. This is for the TI-84 users. And if you click on that, it takes you to the home screen. Now some of you see something that says inderiv, and others see actually what I see here. Okay? So they work the same way. One's just a little bit fancier operating system. So I'm going to go ahead and find the derivative. X is my variable. I really don't want to retype that thing. So I'm just going to go to variables, y variables, functions, y1. Remember I stored it as y1. So we are finding the derivative of y1. Okay? And now I get to pick my x. So this is the part where I never really told you what x we're going to study, so let's just pick a number. I think there's a rad x in this problem. We better stay positive. Why don't we just do 1? That was fast. The calculator evaluated the slope of that goofy graph at x equals 1. The answer is 0.566. You can round it to the nearest thousandth, or you can truncate it and call it 0.565 and just ditch all the other digits. But you must report 3 digits after the decimal, always, on the AP test. If this problem, honestly, I'll be frank, if this problem was just asking for the slope at 1, I wouldn't have done any of the calculus. I would have just grabbed my calculator, and I would have typed that, and gotten the answer. How did I get the y1 to show up? Go to variables, go to y variables, function, and it should be there waiting for you. And that's assuming, of course, that you already typed it in here. Or you can just go back to the home screen, and if you're not too lazy, you can just retype it. So you can just say, okay, I'm taking the derivative with x as my variable, and then just retype the problem. It was sine x squared cos rad x. So sine x squared, and then cos rad x. Just make sure you close your parentheses and all that, and then put the 1 over here. Same answer. Now, for those of you who have the older operating system, things look a little different, and it will look like this. I'll just show you on the video here. I need my smart notebook. Where'd it go? There it is. Okay, so if you have the older operating system, when you first press Math 8, it looks like this, inderiv. And then you can either put y1 or you can write your function, type it up. Okay, and then you put comma. There's a comma button. And then you put x. Then you put comma. And then you put 1. This means, please find the derivative at 1. Don't forget to type the little x here. Okay? That's really important. So, 2 operating systems. This is the old version, and the new looks like this. It goes dd what? Of what? Where? And you type an x here, and a 1 here, and your function here. So the same thing, different way of typing it in. If you have a Casio, I'm not too sure how to do it.
I found it, but it gives me completely,
You might be in,
are you in radian mode?
I think I am in, let me check. I think I'm in radian mode. I'm in radian mode, which is where you want to be in calc always. There's never a time to use degrees. After the AP test, I'll teach you some 3D stuff, and we do use some degrees there. But for now, let's just stick with
5, 6, 5.
radians for everything. So you won't be switching modes all the times. But I did get 0.565 if you're truncating, 0.566 if you're rounding. Did you get the Casio to work?
Yeah.
Very cool. It's a great feature. You can also do it from the graphing screen. I think I might have shown you this before, but it's definitely worth our time. So if you go to y equals again and press graph, you may or may not see much graph. Actually, that's not too bad. We could see a little bit, even on a zoom standard. Look at that period. It's like, I think what's happening is the period is growing. But anyway, this is kind of a goofy graph, but you could study its slopes if you wanted. And so what you would do is just go to second calc. While the graph is on the screen, press second calc. And then dy dx is right there, option 6. And it's waiting for something. You guys know what it's waiting for? It wants me to tell it where to find a slope. So you better pick a positive number because of that rad x, there's no left side at all. Let's just say at 1. 0.566. Okay, that's a more graphical thing. And it also starts blinking right there. Right at 0.56. Right at x equals 1, it starts blinking. You can kind of zoom in, but if you zoom in now, you're going to have to recalculate. Because every time you zoom, you get a fresh graph, and then it won't know that you want to keep looking at slopes. So if you want to actually graph the derivative, because the derivative is a function too, right? If you want to graph the derivative, I recommend you actually turn this off. I recommend you turn this one off. Okay? So you just put your mouse on the highlighter. What am I saying? Put your cursor on the highlighted equal sign and press enter once, and it should de-highlight. So we'll not graph that anymore. Look, blank screen. Okay? And then under it, right here, this is very important. Don't miss this. Go ahead and press Math 8. We're going to graph the derivative graph. Okay? Because the derivative is a function, right? So I'm going to go and put an x there. I'm going to put y1 here, or I can retype if I'm not too lazy. I'm too lazy. I'll just put a y1 there. And what graph, which point do I wish to plot? The slope at 1? I want all the slopes. So I'm going to put an x there. You cannot do this on the home screen. You can only do this on the graphing screen. I'm fooling the calculator. I'm telling the calculator that I want to graph a slope. It can only do one slope at a time. So I'm telling it to go ahead and graph the slope at x. No, it just won't know what x is, so it'll just start plugging in everything. Everything that's within domain. And it will plot all of them for me. It will take a while. It's got to do a lot of thinking. It plots one point at a time. There he goes. This is the derivative function. Its y-coordinates represent the slopes of y. So the original graph's slopes are being plotted out for us. No surprise it's complicated. A little surprised it's bigger. I think your conjecture that the slopes were all less than 1 isn't true. See how it's going? But the original graph was all beneath 1. But the slopes are. The slopes are very steep. Okay, how much of this do you have to know? You've got to know the chain rule today. Some of you learned what a second derivative was today. And maybe you understood it. If not, don't worry about it. Okay? Takeaways today are how to use that chain rule. And hopefully you learned how to do it on the calculator. That's kind of cool. You want to know your calculator really well. By the way, the calculator is not just a luxury. On the AP exam, the calculator is a necessity. There are 18 multiple choice questions where you use your calculator, and they are the hardest ones on the test, some people say. They are very hard questions, some of them. And if you aren't a master at your calculator, you won't get them right. You've got to be able to find y-intercepts, you've got to be able to find intersect points, you've got to be able to find zeros, you've got to be able to find a derivative graph, you've got to be able to find a derivative at a point, antiderivative at a point, or 2 points. There's a lot left to learn. So get that calculator. If you haven't bought one yet, buy a calculator, for crying out loud. Okay? You will not pass the AP test without a calculator. calculator that you are good at. Okay? I've gotten to the point where I can almost do all the AP tests without a calculator. Almost. But only the multiple choice part that requires a calculator. I can pretty much estimate the answers now, but I'm still wrong sometimes. It's not a luxury, it's a necessity. And in 2000, I think it was in 1995, they decided this is it. This is a technological generation, it's going to be a necessity now. And that's when they first allowed the graphing calculator, and the questions were written to require them. You can't really do it without. So, times have changed. When I was a kid, the AP test didn't have any calculator at all. You could use a scientific if you wanted, but it wasn't required. Now it's pretty much required. Okay? All right, so that was a lot of content, but hopefully you learned something new. And you have